We don't have class on Monday. It's school holiday. Make sure you take at least one day off, maybe 2 days off, okay? The only thing you got pending is this student contract next Wednesday evening. And I'll remind you that on Wednesday, you need to sign into Pearson. Your introduction is due the end of September. The anatomical lab is due in 2 weeks. So you got nothing that's really pressing you. I took the other video down because it required a password and it was saved up on the cloud in Zoom. So I took it down and I've reformatted it, and then YouTube is processing it. Plus I have the other video ready from lecture on Monday. So I'll get those posted. Today's Wednesday, they'll be posted by Friday. And then hopefully this video will be posted by the weekend. So you'll have all your videos from chapter 1 and chapter 2, or part 1 of chapter 2. Chapter 2 has 2 sets of slides, inorganic chemistry and biochemistry, and then the macromolecules, which are proteins, carbohydrates, nucleic acids, and lipids. We'll do that lecture next Wednesday, and I'll introduce you to the chemistry lab module on next Wednesday, so don't worry about it. Otherwise, you should enjoy this Labor Day weekend. So you've got, I don't know about your other classes, but you got some days off. And as far as I'm concerned, you need to take some time off. I was always a big advocate of taking time off. Chemistry. Atoms are composed of a dense central area called the nucleus and a region around the atom called orbit, or most recently named orbital clouds. The assumption is that you had at least had chemistry in high school, if not a college chemistry class. I notice some people do and don't. So this starts very elementary, and the chemistry lab module is very elementary and walks you through this. An atom is composed of 3 subatomic particles: a proton, an electron, and a neutron. Protons are positively charged and located in the nucleus. This is the old orbital model. This is the new cloud model, okay? This is the old planetary model. Niels Bohr came up with a planetary model where electrons were in discrete orbits. This new model, the orbital model, is the quantum mechanical model, saying the electrons, rather than being discrete orbits, for this particular shell, are located somewhere in that cloud. Protons have a positive charge. Electrons have a negative charge. They are located out here in either the orbit or in the electron cloud. And neutrons have no charge, and they are located in the nucleus. How dense is this nucleus in relation to the electron cloud? I give this as an example. You put a silver dollar on the 50-yard line of Jaguar Stadium, whatever it's called now, and that's the nucleus, the silver dollar. The first electron shell, where the first electron is the outermost outer wall of the stadium, okay? So the nucleus is very, very, very dense and very small, and the electron cloud is at some distance away. Now, it's still in, nanometers and things like that, but in relationship to size, that's how big it is, okay? Protons and neutrons are in the center. Electrons are in the orbital shells. Protons and neutrons each have 1 atomic mass unit weight, okay? Electrons have weight, but their weight is so small in relationship to what a proton and neutron has that they're insignificant in counts for the atomic mass, which is how much the atom weighs, okay, or the mass of the atom. I give the example, you take a huge dump truck, you weigh the truck, you then fill it up with gravel, you then weigh it again, and that tells you how many thousands of pounds of gravel are there. A piece of gravel drops out. You weigh the truck, the weight doesn't change. You throw the piece of gravel back in, the weight doesn't change. That is a highly exaggerated model, but it's similar to what the model of how much electrons weigh in comparison to what a proton and a neutron weigh. So if you can, if you keep images in your head, then that's the way, I see things with pictures. That's how I see things. And so if we were doing the face-to-face class, I keep my eyelids shut a lot when I lecture because I'm seeing pictures in my head of things. That's the way I see things, uh, or that's the way I think I see things. Uh, but protons and neutrons each weigh 1 atomic mass unit. So if you had 5 protons and 5 neutrons, that element would weigh 10 atomic mass units. Okay, and it would have 5 electrons. We'll learn that in a minute. This is the periodic table. Okay, this is a relatively recent invention. This is the relatively recent version of it. Okay, it's the one we have now. This consists of all the natural elements and all the man-made elements. Okay, if you believe everything came from one source, okay, that there was some type of big bang, okay, or some type of ultimate creation where everything came from one source, then this is the same things that the elements are made up in the other planets, unless we have some that have yet to be discovered. But these are the naturally occurring elements that we have found and the man-made elements. Down here is my favorite element, 99, that's Einsteinium. Okay, everybody knows it. That's probably named after Albert Einstein. Okay, after lead and bismuth, okay, after lead and bismuth, this is polonium. This is, and so these start getting atomic after this. Okay, these start getting very unstable. All right, this is uranium down here. But this is how the periodic table is set up. These are columns and rows, and the columns and rows have names, but this is not a chemistry class. All the columns have similar structure. So hydrogen, lithium, sodium, potassium, rubidium, cesium, and franconium all have similar structure in the fact that they have 1 electron in their outer shell. Okay. They are 7 shells. So if we're thinking about orbital model, or excuse me, the planetary model, there would be 7 different planet orbit shells. Okay. 7 different orbits that we would put electrons in. And they would be orbit 1, orbit 2, orbit 3, orbit 4, orbit 5, orbit 6, or 7. And so these are the rows. Now, these are different in the fact that they have different numbers of protons, neutrons, and electrons. And these have different protons, neutrons, electrons, but everything in a column shares similar chemical properties. Everything in a row shares the fact that they have the outermost shell is the same outermost shell. So everything in row 3 has 3 orbits, orbit 1, or principal energy level 1, principal energy level 2, principal energy level 3. Atomic number, okay? We'll see that in a minute. The atomic number tells you the number of protons in an element. The number of protons determine the element. The number of protons determine the element. Every element on the periodic table is electrically neutral. So if you know how many protons there are, protons have a positive charge, you know how many electrons they are, because everything on the periodic table, as it stands on the periodic table, is electrically neutral. So the number of protons is equal to the number of electrons, but the atomic number only tells you the number of protons. So remember that. That's a gotcha question if you think it tells you the number of electrons. It doesn't. You infer or you deduce that everything on the periodic table is electrically neutral because we know that for a fact. And so if you know the number of positive charges, you're going to have the same number of negative charges. So the number of electrons equals the number of protons. The atomic mass is everything that's in the nucleus. Well, in the nucleus is protons and neutrons. Remember, electrons don't have an atomic mass. Excuse me, they have an atomic mass, but it's so insignificant in comparison to what the proton and the neutron is that we don't use it in the calculation of the atomic mass. So let's do a couple of problems here. And you'll have a problem like this on your test. This is nitrogen. Symbols for element are either a single capital letter or a capital letter and a small letter, okay? Symbols for elements, this is hydrogen, this is lithium, this is sodium. Notice you either have a single capital letter or you have a capital letter and a small letter. Nitrogen has a name underneath it. This is the atomic number, this is the atomic mass. This is an average. When we use it to calculate the number of protons, we just round it down to 14, okay? The atomic number is 7 That means we have 7 protons. We have 7 positive charges. That's the atomic number, the number of protons. No two elements share the same atomic number. Every element is different. If the atomic number was 6, that would be oxygen. That wouldn't be nitrogen. So the number of protons is 7 because of the atomic number. Because every element on the periodic table as it exists on the periodic table, an element, I'll use element and atom interchangeably. An element is a group of similar atoms, okay? An element is a group of similar atoms. So nitrogen is a group of similar nitrogen atoms. They all got 7 protons, okay? Element and atom I use interchangeably. So it has 7 electrons because it's electrically neutral. Well, how many protons does it have? Well, we know that its weight, its mass, okay, and mass and weight are really 2 different things, but we'll use them interchangeably. We know it weighs 14. We know that the only 2 things that have mass, that we calculate with the atomic mass are protons and neutrons. We have 7 protons. So if we subtract 7 from 14, lo and behold, here's our atomic mass. We subtract the number of protons and we get 7 neutrons. They're not always equal. I'll show you an example in a minute where they're not equal. But in this particular case, they are. All right, here's fluorine, okay? Atomic number 9, atomic mass of 18.998. So we round that up to 19. How many protons do we have? 9. Every element on the periodic table as it stands on the periodic table is electrically neutral. What does that mean? That means if you have 9 protons, you have 9 electrons. And I don't know why that thing disappeared. The fluorine mass is 18.99. Let's round that up to 19. We have to deal with whole numbers, okay? All right, we have 9 protons. Our mass is 19. The only things that adds mass are protons and are protons and neutrons. So we subtract 9 from 19. That gives us the number of neutrons as 10, okay? You'll have a problem like this, all right? So just just come back and review this slide. What's an isotope? An isotope is an element which has the same number of protons, but different numbers of neutrons. Has the same number of protons, has the same number of electrons because it's electrically neutral, but it has different number of neutrons. And you already know about that, but you may not think you know about it. We have carbon 12, carbon 13, and carbon 14. Carbon 14 is the one that's used for radioactive dating. So if we find an old manuscript or an old remnant of an animal or something like that, we can use carbon dating to give us an estimate of the age of this material, okay? And we look at the ratio of carbon 12 to the ratio of carbon 14 because carbon 14 is radioactive, okay? So we look at that ratio. I don't know how they do it, but that's what they do it. These are 3 isotopes. Each one of these has 6 protons. Each one of these has 6 electrons. But you can see if you subtract 6 protons from 12, that gives you 6 neutrons. If you subtract 6 protons from 13, that gives you 7 neutrons. If you subtract 6 from 14, that gives you 8 neutrons. So the number of neutrons are different, or the number of neutrons are different. Number of protons and electrons are the same. That's an isotope. Most all elements exist in isotope form, okay? But you can see carbon exists almost 99% as carbon 12, 1% as carbon 13, and a 10,000th, or maybe 2/10,000ths of a percent as carbon 14. Well, how do you get the average atomic mass? You multiply 98.9 times 12, 1.1 times 13, and this times 14. You add them all up together, and that's why you get, for carbon would be 12.001, okay? So that's why you get those odd numbers. They're not because of the isotopes. But when you're dealing with determining the number of protons, you just round them up, okay? Round them up or round them down. Electrons and atomic stability. Electrons swarm in the nucleus around the nucleus in shells, okay? Remember, there's 7 different shells, 7 different principal energy levels. The first principal energy level only holds 2 electrons. First principal energy level, that's the first line, first row on the periodic table. You go all the way across it, there's only hydrogen and helium. It only holds 2 electrons, okay? So the first shell only holds 2 electrons. Second shell holds 8. So the second shell would hold 8. Third shell holds 18. The third shell and thereafter hold more than 8 electrons, except we're only worried about the outermost electrons. We're only worried about the outermost electrons. And the outermost electrons are these 2 columns, okay, and these 6 columns. These are the valence electrons. These are the ones that interact. These electrons in here don't interact so much, okay? So we're worried about the valence. We're not worried about them, but that's what gives us our chemical properties, okay? So when it says that when it says here that the third shell holds 18, however, we're concerned about the valence electrons, which are in the first 2 columns on the left and the last 6 columns on the right. And that gives us a total of 8, which are the ones that interact, okay? That's the ones that interact. So first shell only has 2, second shell has 8, and other shells after that have more than 8, except we're only concerned with those valence electrons. Those valence electrons are the ones that provide stability to the elements, okay? The shells are filled in order, so the first shell is filled up with 2, the second shell is filled up with 8, and then they fill up as they go to the number of electrons that they have, okay? Like when we get to chemistry, if I'm teaching the chemistry, I haven't taught it in a couple of semesters. I teach 1025C and 1032C and 1020 on occasionally. But they'll fill up, until they keep filling up, okay? Atomic bonds, there's 3 types. There's one bond where you share electrons. There's one bond where you take electrons away. And then there's one bond where you got a partial charge and the partial charges attracted to each other. The first one is the covalent bond. That's the electron sharing between atoms. The second one is ionic, where an element takes an electron from another element because it has enough strength to do that. And the third one is an attraction between polar molecules, and that's the hydrogen bond. The hydrogen bond is, all these bonds are very important, okay? All are very important. In the human body, hydrogen bond is very important. This is the strongest, this is the next strongest, and this is the weakest. But in the human body, hydrogen bonds are what holds the 2 strands of DNA together, okay? In our chromosomes, we have DNA, and they're held together by hydrogen bonds. So millions and millions of weak bonds are strong. Covalent bonds formed when atoms share electrons to fill their outer shell. So here's carbon here. It's got 4 electrons in its outer shell, okay? It needs to, atoms are most stable when they have 8, except for the principal energy level 1, where there's only 2 electrons, most stable when they have 8 electrons in their outermost shell, okay? Carbon doesn't have the strength to pull 4 electrons off of hydrogen, okay? But it does have this, it can share, this electron can share that electron, this electron can share that electron can share that electron can share that electron. So we end up with this type of structure, okay? Carbon sharing a pair of electrons with hydrogen, and hydrogen sharing a pair of electrons with carbon. Hydrogen's only got 2 electrons, but remember it's in principal energy level 1, and principal energy level 1, first energy level only holds 2 electrons, so it's stable. And now carbon is sharing a total of, it has 4 electrons and sharing 4 electrons, 1 each from the hydrogen, so it now has a total of 8 electrons. So it's stable too. And so this is methane gas, okay? Elements can share more than 1 pair of electrons. These are 2 oxygen elements, 2 oxygen atoms, okay? Oxygen has 6 electrons in its outermost shell. 1, 2, 3, 4, 5, 6. It can either share share an atom, share an electron with hydrogen. And it would share with 2 hydrogens because that would give it 8. And so that would be H2O. or it can share two pair of electrons, okay? It can share two electrons with another oxygen, and that's oxygen gas. And then nitrogen has 5 electrons in its outermost shell, and it can share three pairs of electrons. And so this is a single bond up here. This is the double bond, and this is a triple bond. This is sharing 3 pairs of electrons, but now nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So this one's stable. This one has 1, 2, 3, 4, 5, 6, 7, 8. So that's stable. So there's a number of ways to obtain stability by sharing of electrons. So this is a strong bond. Next is an ionic bond. You have experienced an ionic bond every day of your life. This is sodium, okay? Sodium has 2 electrons in its first energy level. It has 2, 4, 6, 8 in its second energy level. It has 1 electron in its outermost energy level. So sodium doesn't form 7 bonds. There's only 4 places to bond, 1, 2, 3, and 4. There's only 4 double parking spaces, okay? And so it can't share with 7 elements, okay? And it's unlikely to pull 7 electrons away from somebody else. It just doesn't have the strength. Chlorine, on the other hand, has 2 in its first energy level, 8 in its second, and 1, 2, 3, 4, 5, 6, 7. 7 in its outermost shell. It has the strength to pull an electron away from sodium. So you pull that electron away from sodium. Now chlorine has 8 electrons in its outermost shell, and sodium has this empty shell, which is okay, okay? So it has no electrons there. So now it's not reactive, okay? Because it drops back to this shell and there's 8 electrons there. Normally sodium has 11 protons because it's electrically neutral. It has 11 electrons, and it has 12 neutrons, okay? So that's electrically neutral. If you take 1 electron away from sodium, you now have 11 protons and 10 electrons. That gives you a net positive charge. Chlorine has 7 protons and 17 electrons and 18 neutrons. You grab that electron, okay? And that strength is called electronegativity, but you don't need to know that. You don't need to know that because that's in chemistry. It pulls that away from it. So it now has 17 protons and 18 electrons. 17 positive charges, 18 negative charges, a net negative charge. So we have a net positive charge on sodium and a net negative charge on chlorine. Guess what they do? They attract. Okay, so a net positive on sodium, net negative on chlorine. And then they positive, negative, positive, negative, positive, negative, positive, negative. They form this lattice work here. And this is sodium chloride. This is table salt. So when you're looking at the crystals of sodium chloride, this is what you're looking at. This is what you're looking at. The sodium, the chlorine has taken an electron from the sodium and made it positive. Because it's taken an electron, it's negative, and unlike charges attract, okay? And so that's the attraction there. Hydrogen bonds. Oxygen is a very strong element trying to pull electrons away from another element, but it doesn't have the strength like chlorine does, okay? But what it can do, it can pull, in the case of water, it can pull the hydrogen's 1 electron a little bit closer to itself, okay? So it can't pull it away, but it can pull it a little bit closer to itself. Well, if it does that, the electron that's associated with hydrogen, the blue's hydrogen, the red's oxygen, the electron that's associated with hydrogen is not in the midpoint, just like we looked in when we looked at the carbons and the hydrogen. It's not in the midpoint there. It's closer to the oxygen. So that makes the hydrogen partially positive, not positive, because it still has the electron, it's just not as close as it was. And it makes the oxygen partially negative because the hydrogen electrons pull a little bit closer to it, okay? And so this is a water molecule. The oxygen side's partially negative and the hydrogen side's partially positive. And so with a bunch of water molecules, the oxygen's attracted to the hydrogen's attracted to the oxygen's attracted to the hydrogen's attracted to the oxygen. So you can imagine a sheet of water molecules, okay? Just sheet of water molecules across the surface of water. In fact, that's what water is just a sheet of water molecules, okay? And this is the reason that water has a high specific heat. In other words, we had to put energy into it. We had to put energy into it to get it to raise its temperature. And we had to put a whole lot of energy into it to break these bonds, okay? And so that's why when you got your pot and you're trying to watch it and see if it's, because you're going to put something in the water as soon as it starts boiling, and the heat's there, the heat's there, the heat's there, the water won't boil, water won't boil, water won't boil. You're breaking these bonds so that it can go from a water molecule into steam, okay? So water attracts the polar opposites. So you get surface tension here that allows the water bug to walk on top of water. That allows the water bug to walk on top of the water. Water molecules and compounds, every chemist I know, okay, will use this interchangeably. Technically, a molecule is two atoms of the same to come together. So oxygen, nitrogen is a molecule. Compounds are two or different atoms chemically bonded together, carbon dioxide, okay? But I can tell you that we talk about water molecules, we don't talk about water compounds, okay? So that's the technical definition. You now know the technical definition, but everybody that you talk to, whether it be PhD in chemistry or whatever, will talk about molecules. And so now you know the difference, if you ever had to know the difference. And isomers, what's an isomer? Two molecules with identical atoms, but in different arrangements. Here's an isomer, okay? Here's an isomer of L-alanine and D-alanine, okay? The only difference is this is rotated around, so they're mirror images of one another, okay? They're mirror images of one another. What happens is because the body is very highly specific, one of them might have 95% activity and the other might have 5% activity. We're talking about chemical activity, okay, or availability. Maybe this needs to bond with something else, okay? And so this one may have 95% reactivity, and this one only may have 5% reactivity. And so if you have a genetic defect and you have this isomer present and it's a critical function, and this has 95%, but you don't have that, you have that you could be in some serious problems, okay? So that's an isomer. It has the same number of carbons, same number of hydrogen, same number of everything. Its configuration is the same. It's just a mirror image of the other. And why it's concerning is some of the isomers have different rates of activity, okay? Biochemistry, we're going to look at a little bit about biochemistry, inorganic and organic. There are actually three branches there's several branches of chemistry. Inorganic chemistry deals with non-carbon containing materials, okay? Now, I have to use that with a caveat because CO2 has carbon in it, and there's some things that have carbon in it. But non-carbon containing organic chemistry deals with compounds that contain carbon and hydrogen. They may not be associated with life, okay? They may not be associated with life, but because they contain carbon and hydrogen, they are classified as organic. And in biochemistry has the has the elements and compounds and molecules from inorganic chemistry and from organic chemistry that are associated with life, okay? So that's the difference. Biochemistry encompasses both inorganic and organic chemistry. So if you take a biochemistry class, you'll go into that in greater detail. Well, obviously, inorganic chemistry, water, 79% of the body, but it is a biochemistry compound, amazing properties. High heat capacity, that's what we were talking about. It takes a large amount of energy to raise 1 gram of water 1 degree Celsius. Okay, I used to call it centigrade, they call it Celsius now, I believe, or maybe they call it centigrade or Celsius, I don't know, but it's C, okay? It's a metric measurement. And that's beneficial for us because we go outside into the hot weather. We may pretty much maintain our internal temperature, 97.6, 99.6. Okay, we go outside in the cold as long as we're just as long as we have clothes. We pretty much maintain our internal temperature, 97.6, 99.6. or some kind of range like that. And everybody's range is a little bit different, okay? And so water is unusual in the fact that it requires it has a high heat capacity, okay? High heat of vaporization, that's what we're talking about. The amount of energy extra, okay? You have to put a certain amount of energy to raise it 1 degree, but you also had to put in a certain amount of energy to break those bonds. So that's why it takes extra energy to get water to boil. And if you go outside and you work outside, if you don't sweat, sweat removes, your body will warm up, okay? Your body will start warming up, your internal temperature will start warming up. You know, there's heat exhaustion and heat stroke. And you start warming, but as long as you can sweat, as long as the environmental temperature is less than your body temperature and you can evaporate off the sweat, you can get rid of some of the heat. It's why you look for somebody, if somebody's having heat exhaustion or heat stroke, they're not sweating and they're outside and it's hotter than crap. Okay, that's a bad sign. You need to get them inside and get them to a hospital and let them get cooled down. Okay. And that can happen in Florida. You know, when I play golf, I'm not, obviously not playing much golf now. We're not playing any golf now, but I used to drink water, every hole or every other hole and stay hydrated. And they used to, some of the fancier golf courses would bring around ice towels to put on you, they would bring you a new ice towel and take the old ice towel away. But that's a thing, and so the people that do outside, yard work, roofers especially work in the summer, that has to be a hot job. So high heat of vaporization, polar solvent, universal solvent. Why is it most things in the body are polar, okay? And so in order to transport them from one place to the other, from the GI system to the cellular level, we need to have a solvent, which would be polar because like dissolves like, okay? So the water is polar, and most of the things that we have that dissolve in in the solvent, in the body fluids, are also polar themselves. We have hydrophilic, water-loving. This is a glucose molecule, a sugar molecule being surrounded by water. We have hydrophobic. This is any salad dressing, oil and vinegar. Oil and vinegar don't mix. The only way to mix it is to put it in suspension, by shaking it real hard before you pour it on your salad. Reactivity. When we get to part 2 of the chemistry lecture, which will be next Wednesday, remember, we don't have a class on Monday. When we start putting things together in the macromolecules, when we put monomers, when we put single glucose molecules together, when we put glycerol and long-chain fatty acids together in triglycerides, when we put amino acids together in proteins, and when we put nucleic acids together, what we do is a process called dehydration synthesis. Dehydration means we're going to take a hydrogen here and a water there, send that out, a hydroxyl ion there, send that out as water and form a bond here. So in building up stuff, so we take glucose and fructose, we're going to build sucrose. In building up stuff, we remove water. That's called dehydration synthesis. When we're going to break it down, we're going to do the opposite. We're going to add a water molecule back, add an enzyme, add energy, and we're going to break it down, okay? And so don't worry about this. We'll talk about this in every one of the macromolecules, and I'll keep emphasizing it because you'll have some questions on it, okay? Cushioning, water obviously forms cushioning and surfaces, and and provides lubrication. In plants, water has also unique properties called cohesion and adhesion. A plant does not have a heart. A plant cannot move fluid around, okay? Photosynthesis occurs in the leaves. Photosynthesis is CO2 combined with water, okay, in the presence of sunlight, photons, gives you glucose plus oxygen. Obviously, the leaves can maybe get a little bit of water on, but they don't absorb that much. Most of the water that the plant uses or the tree uses is in the ground. So it has to move that water from the ground up to the leaves, up to the canopy, okay? And so There is no heart to pump that. There are chambers, one going down to the ground and one chamber going up, okay? Water can stick to itself, okay? And water can stick to the side of a surface. You can see that when you see raindrops on your windshield, okay? Water can stick to the side of the surface and water can stick to itself. So when a water molecule is used at the leaf, okay, or water molecules are used at the leaf for photosynthesis, another water molecule is being pulled up and another water molecule is being pulled up. And so that's called cohesion and adhesion. Those are the other properties of water molecules. What's a salt? Anything that dissociates into a positive and negative that does not include hydrogen and hydroxyl. If it's hydrogen or hydroxyl, it's an acid or base, okay? So we put that salt, that sodium chloride, in water, it dissolves, okay? It dissolves into sodium ion and the chloride ion, and so that's an electrolyte. And electrolytes, as a general rule, can conduct electricity. We will go into great detail on muscle contraction and nerve impulses when we get to those chapters. Acids and bases, also electrolytes. An acid, there's the Arrhenius definition that we learned in high school. An acid is a substance that gives up a hydrogen ion, okay? The more hydrogen ions it gives up, the stronger the acid is. The fewer hydrogen ions it gives up, the less strong it is, okay? So here's an example of hydrochloric acid. You put hydrochloric acid into an aqueous solution. Remember, we primarily talk about water because we're talking about the humans, we're talking about the physiological systems. And so notice it completely dissociates. Hydrochloric acid is a very strong acid. Carbonic acid, you know, some of it stays intact, some of it dissociates, okay? It is not a strong acid, okay? So the more it dissociates, the more it comes apart, the stronger it is. The less it comes apart, the less it dissociates. That's what dissociate means. The less strong it is. pH scale. pH of 1 is very strong acid. pH of 14 is very strong base. pH of 7 is neutral. Blood is 7.35 to 7.45 on average. So it's a little bit alkaline, a little bit alkaline. 1 is very strong acid. 14 is very strong base. 7 is neutral. Blood 7.35, 7.45. Bases. Bases are proton acceptors, okay? Well, what does that mean? That means in the old Arrhenius definition, a base was a substance that when put in water would dissociate into some type of positive ion and a hydroxyl ion, okay? This is the Bronsted-Lowry definition. It's a proton acceptor. It's essentially the same thing. What this says is, what is a proton, okay? A proton acceptor. If you think about the hydrogen ion, or excuse me, the hydrogen atom has atomic number 1 and atomic mass of 1, okay? That means it has 1 proton, 1 electron, and no neutrons, because it has atomic mass of 1, and the mass consists of the number of protons and the number of neutrons, has an atomic mass of 1, okay? So if you take the electron away from hydrogen, it has 1 proton, and that's it. And so hydrogen's a proton. Hydrogen is a proton, okay? So that's the next step up a definition of what a base is. Bases are slippery and taste better. Here's a base, sodium hydroxide. We put it in water, it dissociates into sodium and hydroxide. This is the definition we learned in high school. The only thing we're taking it a little step further, it combines with a hydrogen ion from water and forms water, okay? More hydroxyl ions in the solution, the more basic it is. So the more OH you have, the higher number it is. So 14 is a very strong base. That means it's highly dissociated. This is a very weak base down here. It's not very dissociated. So carbonic acid to be on this side and some kind of weak base to be on that side. pH of 7 is neutral. pH is a negative logarithm, so each number changes a 10-fold increase. Why is it negative? Why did they put a negative in front of it? Because if you're doing log 10 of 10 to the minus 3, 10 raised to what power is 10 to the minus 3? What's minus 3? Well, we don't want to say the pH is minus 3, so we put a negative in front of the log, And so that was a minus minus 3, and that gives us a plus number. So that's why pH is a plus number. It is no grand calculation, that minus sign. It was just put there for bookkeeping purposes so that you don't end up saying a pH of -5 or pH of -1. Okay. pH is logarithmic scale, so that means every movement, if we're talking about acidic, down means it's 10 times more concentrated. Okay. So a pH of 6 is 10 times stronger than pH of 7. pH of 5 is 100 times stronger than pH of 7. pH of 4 is 1,000 times stronger than pH of 7. What's a buffer? A buffer, our normal pH is between 7.35 and 7.45. We'd like to keep that in that range, okay? Well, how do we do that? We can do that with buffers, okay? And when anatomy and physiology too, we learn a lot about buffers, respiratory buffers, metabolic kidney buffers, okay? But this is one of the, this is the carbonic acid system. If for whatever reason somebody's not exchanging air very well, their CO2 increases, okay? Their CO2 increases. If one of the reactants or products increases, the system shifts to the other side to take the stress off the system. If you increase the carbon dioxide, the system's going to shift this direction, okay? And the system's going to shift this direction, and it's going to go to carbonic acid, then it's going to go to bicarbonate ion and the hydrogen ion. So if somebody's blowing off CO2, okay, if somebody's not blowing off CO2, they're going to become acidotic. Now, normally you use this to just correct with very minor things. There's a little bit high, then you just shift that, and that shifts us back. If somebody is very acidic, if they have too much of this, then the system's going to shift in the other direction. So if you have a high pH, if you're alkaline, that's going to send the equation to the right. So say you, for whatever reason, went into the store and bought 100 bottles of Tums, okay? You know, all Tums are, you know, it's calcium bicarbonate, sodium bicarbonate, and you know, you got a whole bunch of this, okay, and you got a very high pH, then the equation is going to be shifted to the right to try to keep you out of that, because you want to be 7.35, 7.45. Say you ate all those Tums and you're 7.6, it's going to shift you this way, more acidic, okay? Low pH, acidity sends the equation to the left. So if you have a lot of hydrogen ion, means you have low pH, it's going to send it in the opposite direction. And that's the end of chemistry slides. Oh, no, we don't want to do that. I don't know what it did.